Recently, Inception came out of stealth mode. Inception is a company founded by a couple of professors, one Stefano Emron from Stanford, and some of his co-workers, ex-grad students, colleagues. I'm not sure exactly the relationship, but one person is from UCLA, and then I think there's another Stanford person there. The idea is using diffusion models for large language model text generation, and I think I've been looking at this in the past, so this is not the first time that I'm looking at this situation, and I wanted to say a few words about this. First, from a technological standpoint, it's pretty interesting, and then also I think from a company standpoint. We here at Orange Capital Partners, we don't invest in Series A type startups, but we obviously follow the field. One of our sort of sweet spots where we position ourselves as investors is when technology and science sort of Venn diagram themselves into entrepreneurship and business. So when that Venn diagram overlaps and we can scale technologies to large trillion-dollar type markets, that's where we see ourselves. Our positions are typically public companies like NVIDIA and Tesla, and but knowing about these types of developments helps us generally, of course, understand where technology is going, but also in particular helps us to understand how the companies that we invest in can leverage new innovations. And this is a very good example, because what Stefano and colleagues have done here is really replace the autoregressive nature of text generation to a diffusion generation. And I don't, there's a paper linked in the show notes. That paper is probably about 2 years old, so certainly not what Inception is doing today, but I think it's sort of the intellectual base. And the fundamental idea of the paper is to solve the score matching problem of discrete data. What that means is that if you take diffusion models in general, what diffusion models do is they predict a sort of path from a noisy image to an actual image. So let's say if I want to see a dog sitting on a tree, the model starts with noise and then generally diffuses into a dog sitting on a tree. And it does that by having learned how to do that, having learned literally vectors, many small little arrows that point step by step into the right direction. Now you can do that with images because there is a relationship between pixels. There's a relationship between a dog's fur and its eyes and ears and things like that. Like pixels have inherent relationships, while discrete data like text don't necessarily have that. Now what the authors are claiming and solving is they're saying not really. There is also in text, in discrete data, in other words, there are relationships. They're just a little bit different. They're not sort of in a series. They're not sequential, but they're sort of in the relative positioning. In other words, words that appear in the text have a certain relative probability to each other. So the concrete example, for example, would be if I scramble, if I have a text that the cat sleeps on the sofa. The cat sleeps on the sofa. And the model now is denoising the gibberish sleeps on the sofa. So the gibberish needs to be denoised into cat. Then I could pick cat, dog, pet. But if somewhere else in the text there's the word whiskers or cat food or something like that, then the probability that this word is cat is actually much higher than pet or dog. So this is the fundamental idea. They're labeling their technology score entropy discrete diffusion model, SEDD, and they just came out of stealth mode with Inception, which is a company that is offering text diffusion models for code generation. And what it does in particular, it allows for speed, because now we have sort of freed ourselves from the shackles of the autoregressiveness of models, which is really important if you think about it, because when when you have autoregressiveness in models, then the nature of the model is always going to be this, and then that, and then this, and then that, and so on and so forth. And you do have a little bit of a problem with inference in particular because it's autoregressive. Now, you can solve that problem with the tricks that we've discussed here in the past and that have been discussed in several other papers. The reasoning models, S1, just yesterday we spoke about this also coming out of Stanford, test time scaling. So there are ways to deal with this particular issue of autoregressiveness in models. But the diffusion model offers a whole new paradigm. It's a whole different paradigm, and that's what's so exciting. Again, it allows for parallel processing. So the parallelism is inherent in the model. It doesn't have to be constructed like, let's say, in test time scaling and reasoning. So there's some advantages to this approach. Okay, the paper's in the show notes. The authors talk about it. I think there's some mathematical and particularly engineering challenges that they solve. That's why they came out of stealth mode. And all of this is, in my opinion, very, very exciting and a very nice example of the continuous thought process that is happening in AI, where we're continuously trying to change the nature of the problem so we can get faster, better results for specific situations. So what started with diffusion for images now is morphing into diffusion for text. And I spoke with the head of AI at Google. I forgot his name. I think last year at a conference, he spoke about this when I asked the question whether the autoregressive nature of models is here to stay. He said, yes, for now, but there are some new ideas, for example, diffusion for text. Let me give a brief overview over what diffusion for text actually means and where it comes from and what the core ideas are, because I think it's worth going back and recalibrate ourselves of where we stand. Diffusion models originate in physics, actually. It started with physics when the problem that was solved there was how does heat diffuse on a specific material. For example, you put a hot plate into cold water, or the other way around, you put a cold plate into hot water, and then the heat dissipates in that plate. And there's a certain score function that the energy follows, score function being a bunch of little vectors that point into a certain direction with a certain speed and force and things like that. And all of that together solves the problem of how does this heat dissipate on that surface. That idea was taken by a couple of original authors probably about 10 years ago and applied to image generation and diffusion. And I think one of the big models was called stable diffusion back then, really became like a big deal. And it competed with, let's say, GANs and things like that. So the generative nature of images started even before ChatGPT was successful. And probably part of the reason that image generation was first was because there's a lot more structure in images, apparently, than there is in text. So when a dog sits on a tree, there's a lot of symmetry there. And you can solve some of the problems with convolutional neural nets to take account of that symmetry. And all you have to do is understand when the symmetries break. So when the tree turns into a dog and the dog turns into a sky or something like that. So there are these breaks of symmetry which define what things are. And I mean, this goes really back to physics, that everything in physics, every matter is actually just a break of symmetry. Now, having said that, the question now comes up, okay, why do we want to use diffusion for text? What's the advantage? The authors point out that the problem with diffusion the problem with autoregressive models, so the problem with the idea of having this sequential probabilistic outcome of tokens, predict the next token kind of model. The problem with that is that it's inherently slow and inherently dangerous for mistakes. Because if you make one small mistake in the beginning, you can end up in a bad place, akin to if you want to shoot a rocket to the moon, you have to be very precise. And if you make a little mistake here on Earth when you target, you will not end up on the moon, but somewhere very, very different. So it's the same idea with autoregressive models. So if you could somehow overcome the autoregressiveness of the model, then maybe you could have better results. That's the fundamental idea. And there's a good reason why diffusion models were first applied in images, again, because images have structure and they're actually better than autoregressive models. But ChatGPT was, sort of founded on the idea of autoregressive models, on the transformer architecture, that for better or for worse. Now, that was a big success, and we are actually living today in a world where that is still being used. Now, what Inception is doing as a company is trying to change that by using diffusion for text generation. And they're doing that by using a diffusion architecture and solving one fundamental problem, which is the score function in a discrete model has different properties because the discrete nature makes it inherently difficult to calculate a score function. It's in technical ways it's an oxymoron because you need continuous data for score functions. So what the authors do is they do a relative score function. So they kind of, instead of trying to understand that the word, the sentence, the cat sleeps on a sofa, there is no continuous score function that goes from the to the cat to sleep on the sofa, right? There's no continuity there. It could be the man is shooting a bird, the car is driving, or the cat sleep. Like there's no. However, in the context of all the words together, there is a score function to be calculated, and that is what the authors are doing. So the cat sleeps on the sofa. It could be the cat, the pet, the dog. But if somewhere else in the text we find the word whisker or the word cat food or something like that, then lo and behold, we actually know that it is a cat, and the probability of cat goes up and the perplexity comes down, which is the measure of how good a model is. In other words, can it put a very high probability for cat and very low probabilities for any other words? So that's the fundamental idea, and it really solves two big problems. One is it allows for parallelism because now we have the opportunity to solve this in parallel versus autoregressive, and more importantly also we have the opportunity to fix problems in the beginning. So it's not even like, this is not I'm shooting a rocket to the moon type problem. This is I have a trajectory from here to the moon, and if there's a problem somewhere, I can fix it right away because the trajectory is related to each subsection of the trajectory is related to the other subsections. So if there's a deviation somewhere, we can immediately fix it. So that's why they're able to generate a lot more tokens per second. So they're much faster, and they have the ability to fix problems much faster as well. So those are the two big advantages, in my opinion, of this diffusion for text model, which is I think more important than it might. Maybe I'm not able to bring across how important this is. The fact that I'm actually doing this episode hopefully already underlines the importance of this. But I want to put this more in a general context. First, it's great to see a couple of academics actually succeeding with a company. It's also great to see that there is new innovation in this field. And for us at Orange Capital Partners, since we're not Series A investors, we have our focus is on understanding where the technologies are going and what's possible, and where the Venn diagram between science technology and business actually lies, because this idea of diffusion for text could improve drastically, for example, code generation, which could drastically improve productivity, which could drastically improve real economic growth. So there's a real relationship here between an innovation that happens in an office somewhere at Stanford University and the actual real economy. So there's a connection here, and it's not straightforward. And maybe, to use pun intended here, it's it's not necessarily autoregressive, and we don't have a clear trajectory. But in a diffusion type thinking, we could say, look, as a whole, all these things are related to each other, and we will see impact. So to summarize, Inception coming out of stealth mode, congrats to the people in the company, but also, more importantly, also really pay attention to these types of developments, because I think that's where the future of AI is going to be. It's going to be in bringing out faster, more elegant models to solve for speed, parallelism, and error correction. Thank you.